Hello everyone, we are presenting our CSE 106 mini project on binary search and followership graph analysis. Our group members are Lailun Nahal Namisa, Janatul Firdaus Dipamoni, and MD Habibur Rahman Fahad. Our project had four main objectives. First, to analyze the time complexity of binary search and check if it matched the expected login behavior. Second, to simulate a followership graph as a directed graph. Third, to measure in degree, out degree, and SCCS or strongly connected components. And finally, to connect the theory with practical experiment and plots. For binary search, we designed a simple experiment. We generated sorted arrays of size 10k, 20k, 30k, 40k, and 50k. On each array, we performed 1000 random searches to make sure the results were averaged and fair. We then recorded the average search time in milliseconds and plotted those values with a trend line. This method allowed us to see how runtime changes as the input size increases. This plot shows that as n increases, the average search time also increases, but only slowly. The curve follows a logarithmic pattern, not a straight line, which matches the theoretical login complexity. This confirms that binary search remains efficient even with very large inputs. For the social followership simulation, we modeled a network as a directed graph. We tested it with different users count 500, 1000, 1500, 2000, and 2500. Each user was randomly connected to follow 1 to 5 others. We then calculated the in degree, out degree, and the number of SCCs. Finally, we plotted the SCC count against the number of users to study how connectivity grows with the network. The plot shows that as the number of users increases, the SCC count also increases. This means larger networks naturally create more tightly connected subgroups. Where each user can reach the others, it reflects how real social networks become more complex as they scale up. Now, here we have the binary source code and sample output. The key idea is simple. Check the middle element. If it matches, stop. If the target is smaller, search the left half. If larger, search the right half. This Haveling process explains why the algorithm runs in logarithmic time. For the followership graph, the code creates n nodes, adds directed edges based on 1 to 5 random follows per users, compute in and out degrees and SCCs, and finally plots the SCC count versus users. This turns the abstract graph theory idea into a concert experiment we can visualize. To conclude, our binary search experiment confirmed the expected login runtime. The followership graph simulation showed that SCCS increase as the network grows. Overall, our results clearly validate the theory with practical data and visualize experiment evidence. Thank you everyone for listening.